Hello, and welcome back to Unearthing the Past. In this section, we'll explore how archaeologists actually work in the field, from spotting potential sites to uncovering them layer by layer. In today's lecture, we'll focus on how sites are discovered and surveyed. Then, in the next section, we'll dive into excavation methods and the key principles that guide archaeological investigations. So, let's get started. Before any excavation begins, archaeologists need to understand the landscape. Where should they dig? What might be buried there? Take this alpine landscape, for example. At first glance, most of it appears natural wild mountains, dense forests, rolling hills. But much of what we see is shaped by human intervention. Pastures, houses, roads, all of which have transformed the land over time. Even woodland can be carefully managed. Within this context, remains of past settlements may have vanished from view, hidden by erosions, vegetation, or later development. What looks natural might in fact conceal deep layers of human activity. This is where survey comes in, the process of identifying, recording, and mapping potential archaeological sites across a given area. Surveys help archaeologists spot patterns in surface finds, detect buried features using remote sensing, and understand how a site fits into its wider environmental and historical context. Survey is the first step in transforming the landscape into archaeological data, turning observation into evidence and terrain into insight. In short, survey is where we begin asking the right questions and where the journey of discovery truly begins. There are several kinds of archaeological survey, including fieldwalking, geophysical and remote sensing, and aerial methods such as photography, drone surveys, and satellite imagery. Field walking is one of the most traditional and widely used methods in archaeological survey. It's a surprisingly simple idea. Archaeologists walk across a landscape, usually in straight, evenly spaced lines, carefully scanning the ground for any surface finds. These could be pottery sherds or pieces of worked flint, tile fragments, or even scattered building materials like fragment of mosaics, for example. By recording where these finds appear, we can start to map out patterns, and from those patterns, we can begin to interpret the possible location, size, and even nature and chronology of buried archaeological sites. In other words, field walking helps us build a picture of what might lie below the surface without having to dig a single trench. This method is especially effective in plowed fields, where ancient materials is likely brought to the surface by farming. Geophysical investigation is the second major area of archaeological survey, using non-invasive techniques to detect what lies beneath the surface without excavation. Methods like magnetometry, ground penetrating radar, also known as GPR, and electrical resistivity allow archaeologists to see underground features by measuring physical contrasts in the soil. These tools can reveal walls, ditches, roads, and even graves, all without putting the spade in the ground. Magnetometry is a fast, non invasive method used to detect buried archaeological features by measuring subtle changes in the Earth's magnetic field. Human activity, like digging ditches, building walls, or lighting fires, alters the magnetic properties of the soil. For instance, burning in a hearth or a kiln can permanently change the magnetism of the surrounding ground. Even filling a trench with different material creates magnetic contrast compared to undisturbed soil. During a survey, archaeologists walk over the area with a magnetometer, which records tiny variations in magnetism beneath the surface. These readings are then processed into a visual map where anomalies show up as light or dark patches. These patterns often point to buried structures such as ditches, pits, or foundations, helping archaeologists target their excavations more precisely. GPR works a bit like a sonar or an underground version of an echo. It sends short bursts of high frequency radio waves into the ground. When these waves hit something buried, like a wall, a floor, a grave cut, or even changes in soil, they bounce back to the surface. A receiver on the device records how long it takes for those signals to return. Different materials reflect the signal in different ways. So, solid stone might give a strong reflection while loose soil gives a weaker one. By collecting these reflections across the grid, archaeologists can build up a kind of 3D map of what's underground, showing not only that something is there, but how deep it is and what shape it might be. Electrical resistivity works by passing a small electric current through the ground to measure how strongly the soil resists the flow of electricity. Different materials like stone, soil, water, or metal conduct electricity differently. Electrodes are inserted into the ground in a grid pattern. A small current is sent between them, and the instrument measures how easily that current moves through the soil. If the current flows easily, the material has low resistivity. That could indicate moist soil, a ditch, or a pit. If the current struggles to pass through, the material has a high resistivity, which might signal solid features like walls. By taking hundreds or even thousands of these readings across the site, archaeologists can build up a detailed subsurface map showing buried features based on how the soil conducts electricity. Sometimes, however, archaeology is easier to see from further away, from above. Aerial photography, drones, and satellite imagery reveal features like crop marks, soil marks, shadows from buried structures. These methods are especially useful over large or inaccessible areas. Crop marks are an incredibly useful tool in aerial archaeology. They reveal differences in plant growth caused by what's buried beneath the surface. Imagine standing in a field of wheat. In one section, the wheat is growing taller and denser. That's likely because it's above a field-in ditch, where the soil retains more moisture and nutrients. In contrast, if the wheat is growing above a buried wall or structure, the plants tend to be shorter and sparser, as there's less moisture and less room for the roots to grow. These differences are often hard to spot from the ground, but when seen from the air by plane or drone, they become much clearer. Areas of lush growth appear darker, while sparser patches look lighter. The resulting patterns are what we call crop marks, subtle visual clues that hint at what's hidden beneath the landscape. Take this iron village, for example. You can see a roundhouse, a ditch, and a wooden palisade with stone foundations. After 2000 years, these features have long since disappeared from the surface, but they have left behind subtle traces on the ground, maybe a slight ridge, a shallow depression, or a faint outline where a ditch once was. To the naked eye, walking through the field, there's often nothing striking to see. But in the right conditions, these buried features affect how crops grow above them. From the air, these differences in vegetation form patterns, and those patterns can reveal the entire layout of a lost settlement. Another powerful tool in modern archaeology is satellite survey. This involves using high-resolution images taken from space to help identify archaeological features on the ground, sometimes across vast and otherwise inaccessible areas. Think about very thick forests, for example. Satellites don't just take photos in visible light, they can also capture infrared and multispectral data, which can pick up things we'd never notice with the naked eye, like subtle changes in vegetation, soil moisture, or ground temperature. These differences can reveal all sorts of buried features, walls, roads, ditches, and ancient field systems, even when nothing is visible at ground level. It's incredibly useful for spotting crop marks or monitoring how landscapes change over time. Satellite imagery is particularly valuable in areas that are too large, remote, or politically unstable to survey on foot. It allows archaeologists to identify new sites, track damage or looting, and explore human activity at the landscape scale. LiDAR is one of the most exciting tools in modern archaeological survey. It works by firing laser pulses from aircraft or drones down to the ground. These pulses measure the landscape in an incredibly fine detail, and one of its biggest advantages is that it can see through vegetation. This means archaeologists can detect tiny changes in elevation even in areas covered by dense woodland. Features that would be completely invisible at ground level suddenly stand out when viewed through LiDAR data. Along Hadrian's Wall in the UK, for example, this technique has revealed 3 previously unknown Roman military camps and more native settlements than archaeologists had expected. These discoveries offer valuable insights into the early phases of Roman military occupation in northern Britain and suggest that the frontier zone was far more populated and dynamic than previously believed. Once a promising site is identified, archaeologists ask a few key questions. Is it worth digging? Is it the site at risk, for example, from construction or erosion? What kinds of research questions could excavation help answer? So, survey isn't just about finding site, it's about making informed decision and planning responsible targeted excavations. And that brings us to the focus of our next lecture, how archaeologists excavate and what principles guide that process. Stay tuned.